This conference will now be recorded.
Yeah. Okay, fine. Let us move on to the class image segment class and image segmentation now. So as I said on the last on the other day, I'm repeating this particular image segmentation part one, and in the image segmentation fourth chapter, total we have two parts. One is on image segmentation, another one is on morphological processing. So here it is the syllabus you have as per the JNTU curriculum, and in the fourth chapter, if you observe, image segmentation is the part one, and morphological processing is the second part. And morphological image processing is already discussed for A section as well as B section people. But for B section people, image segmentation part is also over. But anyhow, I'm repeating the same for the sake of A section people. And image segmentation, in the image segmentation total we have detection of discontinuities, edge linking, and boundary detection, thresholding, and region oriented segmentation. Only few topics we have, limited topics, right? So here in the image segmentation, right, so we have detection of discontinuities, edge linking and boundary detection, thresholding, and region oriented segmentation. So first of all, what is segmentation? So in the name itself, you might have heard about the word segmentation. In the dictionary meaning of segmentation in the sense, just divide divide into the parts. That is called segmentation. Dividing into the parts is called segmentation, right? Now, here, as I said, image segmentation divides an image into regions that are connected and have some similarity within the region and some difference between the adjacent region. So here, I'm saying that I'm just segmenting the image into parts. How do you segment? Is the segmentation way like physical segmentation? Physical segmentation in the sense, if I have the image, I'm going to divide either in the vertical direction or in the horizontal direction. That is called physical segmentation. So it is not a physical segmentation. That segmentation is based on the connectivity, the regions. So here we are just dividing the whole image into regions. How the whole image is converted into the region? Here we are going to separate the pixels which are connected, and we are going to keep away the pixels which are not connected. So in the sense, so we are going to take the similar pixels together to form a region, and we are going to separate the different pixels from the regions to into the other regions, right? So that is called segmentation. So the final goal is usually to find individual objects in the image. For example, I have captured the image. I have captured the image. In the image, I have, when I capture the image from the satellite, in the image, I have some rocks and some water resources and some trees and human beings, right? So here I have a lot of information in the image. So that is to extract the content from the image, the objects from the image. I'm going to use this particular procedure, image segmentation first. So where I'm going to segment the image based on the similarities or based on the connectivity between the pixels, and therefore I can separate the objects. That is the basic idea behind this particular image segmentation, right? And now, for the most part, there are fundamentally two kinds of approaches to segmentation. One is discontinuity and similarity. That is, similarity may be due to the pixel intensity, color, or texture. So based on the similarity, I can segment the image. Yes, the similar object, that is the similar pixels, will be the pixels of this particular object. Or based on the discontinuity also I can segment, and there is a discontinuity between the pixels at this particular point. Yes, you can separate the regions over there. That is, either based on the similarity or based on the discontinuity, you can apply the segmentation. Similarity may be due to the pixel intensity, color, or texture. Differences in the sense sudden changes. That is, if you have any high frequency component, that is called sudden change. And especially sudden changes in the intensity along the boundary line, which can be called as an edge of an object. So wherever you have the discontinuity, and there you can just end the region. And at that particular point, you can decide the edge of the or boundary of the region, right? And finally, what I can conclude is segmentation algorithms are area oriented instead of pixel oriented, or region oriented instead of pixel oriented, right? I am not segmenting based on the pixel. See, physical segmentation is not applied here. First one is, how do you identify the discontinuities, and how many types of discontinuities we have? We have point discontinuities, line discontinuities, and edge discontinuity or edges. So point discontinuity in the sense, for example, I have a plain paper, and in the plain paper, I have a particular dot here. So here that is called discontinuity. And to identify the discontinuity, and we need to follow a procedure. That particular discontinuity is called point discontinuity. So usually these point discontinuities can be observed in the case of noise additions, that is salt noise or pepper noise. You can find the point discontinuities in the image with the noise, right? And how do you identify the discontinuity? So the most common way to look for the discontinuity is to scan the small mask over the image. So whenever you have the image, and if you have any dot, a discontinuity, and I'm going to take a mask by moving the mask on the particular image, and up to that particular discontinuity, the resultant of the mask will be different, and at that particular point the resultant of the mask will be different. What do you mean by resultant? The resultant is nothing but r. R is equal to, whenever if I take a mask as a window, the window will be having the values from w1 to w9, and if I keep that particular window on the image, that image will have the pixels, and that window will be placed on the pixels of the image, and those pixels let us consider from Z1 to Z9, and a set of pixels from Z1 to Z9. When I keep that particular mask, and the product of the window value and pixel value can be taken and summed together to find the resultant, that is R. That is R, right? So based on the R, you can decide whether there is any discontinuity or not. So if R is same at every point, no discontinuities can be, no discontinuities observed. If you find any difference in the R, so which type of difference? Ultimately, you cannot find the same R value everywhere. Why? Because even if you take my palm, in my palm, at this particular area, if you observe, this particular area is appearing as similar. That is, there is no change in the adjacent pixel values. But if you move the mask on this particular part of the palm, you may, that is, it is not different, it doesn't have any different regions, and this particular whole region belongs to a single object, right? And you may not have the R value as same, but these are all the pixels belongs to a particular region. And if you observe here, a line can be observed here. If you go on, that is, if you move the mask along this direction, at this point, ultimately the R will be changed. That R will be changed. The R is changed by how much amount? We need to keep a threshold. Why? Because here also you cannot find the same R. Therefore, you need to keep a threshold to decide the discontinuity, and that is called T. T is called a non-negative threshold to identify the discontinuity. If at all, if that particular R is exceeding the threshold value, you can decide that there is a discontinuity in the image. Which type of discontinuity? Point discontinuity. That is, this particular mask is used for identifying the point discontinuity, right? And moreover, line detection after the point discontinuity, and you may also have in the image line discontinuity. And how do you identify the line discontinuity? Here, the only slightly more common than the point detection is to find 1 pixel wide line. And earlier, I have given an example, that is a dot in the white sheet. If I take a line in the white sheet, that is called a pixel wide line. That is called line discontinuity. That is called line discontinuity. How do you identify the line discontinuity? That is, for example, if I take my face, and at any point I may find a mole here, and that particular mole is called a point discontinuity. That is not separating any two regions here. If I take a line here, if I take a line here, that is at this particular eyebrow point, I have the line discontinuity. That is, there is a separation. Or else, if I have any scar here, any scar, and it also comes under line discontinuity. And how do you identify that particular line discontinuity? Again, by using the same method, that is by using mask. And how many types of masks you can use? You can use horizontal mask, vertical mask, horizontal or vertical or diagonal mask. That is by moving the mask along either horizontal direction or vertical direction. Here you can identify the line detection by checking with threshold value, right? And it is an example. For example, here, if you observe this particular internal image of an IC, let us take, or what you call motherboard IC, if I take, right? So here there is a bondage between these two places, right? So here there is a discontinuity that can be observed here. For example, here it is the discontinuity. At this particular value, we have the similarity between the pixels, but here you have the discontinuity between the pixels, right? So here I want to identify only a mag, that is more where we have more discontinuity, that is these thickest values I would like to identify. There I can keep the threshold. I can keep the threshold. Based on the threshold only, you can decide whether it is the required discontinuity, line discontinuity, or unwanted line discontinuity for segmentation process. Simple example also taken here. That is, if I have the ideal image, ultimately you can easily identify the discontinuity, but in fact we don't find any ideal type of the images. In the real-time images, you can find this type of binary images, these type of binary images, and it is called discontinuities. And here you have to keep a threshold. You have to keep a threshold, and you have to say that it is the discontinuity point, right? So anyway, here simple examples are taken, and moreover here, so next one is edge detection. Edge detection. The same example can also be taken for edge detection here. So here I have two regions. So in the ideal case, I cannot find, in the ideal case, edge can easily be identified. But in the real time, you cannot identify the edge like this. For example, if you have the my palm image similar way, at this particular point, it is the pixel values are different. At this particular point, the pixel values are different. It is one region, it is another region. It is front side of the palm and it is back side of the palm. And where is the separation point we have? And this particular line is the separation point. But if you observe this particular line, is it like ideal or ideal image? No, the change in the pixel values are not in the drastic way, and they are just changing in the ramp form. That is, if you observe the second image, this is the example for this. That is, the pixel change is in the ramp direction, that is in the ramp way. That is, there is no sudden change in the pixel values, right? So here, there, the best method I use to find the edge is in the image enhancement we might have studied. You might have studied. That is, In the image enhancement, we are supposed to find the edges to enhance some part of the image or some region of the image. And there, you might have studied about the gradient operators. The gradient operator is the one which is used to identify the change in the image, the change. So gradient in the sense, nothing but gradient is for what? You might have studied even in other subjects also. The gradient is basically used to identify the change. Why? Because gradient is the value which is taken by taking the differentiation along the x direction if it is a two-dimensional along the x direction and y direction. In both the direction, we observe the change to find the gradient. That is called gradient. If I take gradient as del f, if I take f of x comma y is the function, the del f equal to dou f by dou x plus dou f by dou y. The change along the x direction and the change along the y direction can be considered for finding the gradient value. The gradient value is used for identifying the edge, right? So here, for example, here, how do you identify? If I take the first derivative, it is the gray level profile. If I take the first derivative, it is giving the maximum value only at the change position. So here it is saying that at this particular point, I have the edge. If I find the second derivative, even I can find the spikes, and it shows that from this direction, where is the edge? From this direction of the image, where is the edge? Right? So you can find the edges from both the directions by using the second derivative. Another example here taken here, and this edge detection is may not be possible if there is any noise in the image. If the noise part is more, and it will be difficult to find the edge. Difficult to find the edge. And some examples are taken here. That is, the image is added up with a noise. Which type of noise? Gaussian noise. And if the Gaussian noise standard deviation is, the variation is improved or increased, ultimately it will be difficult to find the edge. For example, 1, 2, 3, 4. Out of the 4 cases, the first case is ideal case, that is sigma equal to 0, mean equal to 0, and that is the noise effect is 0. So in such a scenario, you can easily identify the edges. If at all, if the noise value is increased and it is becoming difficult in identifying the edges, if noise content is more, here you can observe the edges are not at all detected here, right? So here, in the case of noise, the edge detection process will be difficult, and it is some cases may not be possible to identify the edges even. And there you need to remove the noise, and then you can go with the edge detection, right? So as I said, gradient operators are used to identify the edges, right? So it is the way to take the gradient operator. One is along the horizontal direction, the change along the horizontal direction. Another one is the change along the vertical direction. And usually the magnitude part is used to, that is, this magnitude decides the amount of change, whereas the direction can be taken like this. And the magnitude quantity gives the maximum rate of increase of f of xy per unit distance in the direction of the gradient. So what do you mean by this del f? Here this del f will give what? The maximum rate of increase of f of x comma y per unit distance in the direction of the gradient. This gives the direction. In which direction we have more gradient can be observed by using this direction and magnitude values, right? And here in the image enhancement, you might have studied about these particular gradient operators for the edge detection process. Usually here, to identify the edges, we are not going to do anything here. We are going to keep a mask here, and by keeping, that is, by moving the mask along the image, you can identify the edges. How do you identify? Yes, by keeping the mask here. That is similar process of convolution. I am going to find the resultant by moving the mask over the image, and based on the resultant, by comparing the threshold, I can decide whether there is any edge or not. And how do you decide the mask here? That mask is designed using the gradient operator. And here in the enhancement, image enhancement topic, You might have studied about different operators or different masks which can be prepared by using the gradient values. And the examples are Robert operator, Privet operator, Sobel operator. And these are all the masks to identify the edges. And these masks are also there in the image enhancements topic. Right? Now, so some examples. So for example, here we have the original image and it is the binary, sorry, not binary image, a gray level image. Why? Because the pixel intensity values are not similar, not either 1 or 0 here. The pixel values are changing from 0 to 255. It is the gray level image. If I apply the gradient operator to find the change along the horizontal direction, and this will be the resultant, and it results only the changes along the horizontal direction. Whereas if I take, that is along the vertical direction, if I take, it is the resultant, it shows only the changes along the or edges along the horizontal direction, the vertical direction. It is for horizontal direction, it is for vertical direction. And if I combine the both, I can identify the edges of the entire image along the horizontal direction, along the vertical direction, right? That is, the above one is used by using the filter or mask. And if I improve the mask, for example, a 3x3 mask is used to identify the edges here. And now if I improve the mask, that is, if I take a bigger filter, that is 5x5 mask, still it can be improved in the edge detection process, and the more edges can be identified here, right? Already this part is discussed in the image enhancement only, but again here my target is to segment the image, and for that I need to identify the discontinuities, that may be point discontinuity or line discontinuity or edge discontinuity. I'm just explain the procedure to identify the edges, right? And even I can use the Laplacian mask to identify the edges. In fact, the Laplacian mask will not work whenever there is a more noise. In fact, but anyway, it can give the proper edge if you identify the zero crossing. If you identify the zero crossing here. So it is the Laplacian mask to identify the edges. So here, so how do you design the mask here for identifying or for developing the gradient mask? And we have one example here by using the Gaussian type of function. It is not Gaussian function, it is like Gaussian type function. So it is, this particular function is taken here, and we are going to convolve. I have the image and I have the image. That image is going to be convolved with the Laplacian of this particular Gaussian function. And the Laplacian of Gaussian function can be represented like this. This is the Laplacian of Gaussian function, defined as h of r equal to minus e power minus r square by 2 sigma square. And you can easily find. Why? Because you know how to find the Laplacian, how to find del square hr, right? You might have studied in the EMTL, finding of del square of f of x comma y or f of r comma theta, like this, right? And it is Laplacian of Gaussian, and this is this can also be called as LOG. So LOG is the is very important function which is used to identify the edges, right? So this particular LOG is going to be convolved with the original image to identify the edge. Here, in fact, in the real time, we are going to design a mask based on this Laplacian of Gaussian. So here the Laplacian of Gaussian sometimes is called Mexican hat function. Why? Because the shape of this will be like Mexican hat. I'll show in the next slide. It also can be computed by smoothing the image with the Gaussian smoothing mask, followed by the application of Laplacian mask. So in the different way also you can apply. So instead of using the direct del square HR, first you can use the smoothing filter. That is, you can apply the low pass filter and then you can apply the Laplacian mask. So it is the del square h form, del square h representation in the pictorial manner, right? So it is appearing as a Mexican hat, right? So based on this, a mask is designed. Using this mask, you can identify the edges. And not only this, one example is LOG for identifying or for detecting the edges. LOG is the example for edge detection. Using the LOG, you can identify the edges. Here, as I said, Sobel operator, Privet operator, and usually the widely used one is Sobel operator. And therefore, the example is given like this. If I use the Sobel operator, it is the original image. And in the image to identify the edges, I am using the Sobel operator. If I use the Sobel operator, it is the resultant, right? It is the resultant. Even I can use another Laplacian operator also to identify the edges, right? Some example. Next one is, first one is detection of discontinuities. For the image segmentation, the first task is detection of discontinuities. Therefore, we have discussed point detection, line detection, and edge detection. And the next one is, for example, here I have identified the edge. Very good. But due to the problem in the capturing process, or due to the problem in the edge detection process, if there is any breaks in the edge part, or if there is any discontinuity in the edge of the image, then how do you decide whether the two edges belongs to the same object if there is any discontinuity in the edge? And you need to link up the edges to identify the object. That is the next task. So that is, detecting the edge is the one criteria. After detecting the edge, if there is any breakups in the edge of the object, the linking the edge is also a major criteria here. That is called edge linking, or the complete boundary detection of the object. Complete boundary of the object. For example, here, if my image is taken, right, one image is captured here, and these are called edges. By using the edge detection technique, up to this the edge is identified. There is a breakup here, and from here the edge is detected, and you can say that it is a particular object only you have the continuation in the edge or continuation in the boundary, right? So therefore, the boundary detection and edge linking is also a major criteria in the case of image segmentation. And for edge linking and boundary detection, we follow two methods. One is local processing, the other one is global processing, right? Local processing and global processing. Local processing is a easy method. Local processing, that is, in the local processing, basically we consider two properties of the edge points. One is the magnitude, that is magnitude of what? The strength of the gradient operator. That is, whenever you apply the gradient operator to detect the edge, ultimately you can find some magnitude of the gradient operator at the edge point. At the edge point. At the edge point, you take the gradient operator and the direction of the gradient operator. That is, whether it is moving downwards or upwards or at other directions. Why? Because, and based on that only, I can decide the boundary, right? So here, therefore, we consider basic two properties. One is magnitude of the gradient operator, other one is the direction of the gradient operator. And this is usually done in the local neighborhoods. That is, for example, at this point I have the edge, and after that I have the edge here. There is a breakup here, and I know the magnitude, and I know the magnitude here. I'm going to compare these two, and if they are absolutely same or almost similar, then I can combine here. And I can use local neighborhood. That is, I'm going to take the value of this particular pixel, gradient value of the particular pixel, and its gradient of its neighborhood pixel. And by comparing this, I can decide whether it is the boundary or edge, right? That is called local processing. Another one is adjacent edge points with similar magnitude and directions are going to be linked. So how do you check? That is gradient of f of x comma y and gradient of this f of x naught comma y naught, and these two are going to be compared, and these two values are going to be compared. If the difference is less than the expected threshold, then you can say these two belongs to the same edge or same boundary, right? Example here. For example, it is the image captured from the uh, traffic camera, that is traffic light camera, right? So here, if I apply the gradient here along the x direction, this is the resultant. Along the y direction, this is the resultant. And here, this particular number holder is unable, that is, we are unable to identify the edge of the number holder. That is how long it is extended, number holder, right? So here, by using this particular edge linking procedure, we are able to retrieve the boundary of the number holder, registration number holder, right? Next, in this, another one is global processing. Another one is global processing here. So in the global processing, first one is values, local processing. In the local processing, we take the pixel values, pixel magnitude values and then using its local neighborhood, right? But now we go with global processing. So in the global processing, the points are linked by determining first if they lie on a curve or a specified shape, curve of specified. That is, we use the global relationship. Global relation. That is, if any two pixels are considered along the edge, that is, it may be one edge, it may be another edge. My target is to link up the two edges if there is any relation. Right? So what I'm going to do here, I'm going to check whether these two are lying along a curve of a specified shape or not. That shape may be like this, or that shape may be like this, that shape may be like this. In any shape, whether these two belongs to or lie on a curve of a specified shape. But here, unlike the local processing, we use the global relationship between the pixels. That is called global relationship. Global relationship. Here, how do you identify? For example, I have n points in the image. And in the image, if I have endpoints, suppose that we want to find subsets of these points that lie on the straight line. I have one pixel here. Out of the endpoints, one pixel here. And I would like to identify the pixels similar to this pixel. Maybe this point or right side of this or left side of this or below of this or above of this, anywhere it may be. And these are all the pixels of subset of pixels that will be there in the subset of nth pixel. So like that, if I have n pixels, all the pixels will be having subsets. That is, I would like to identify the subsets of the pixel for linking up the edges. Right? For example, here I have two pixels. So between the two pixels, I can draw the straight line. And by drawing the straight line here, I am going to check each and every pixel. I am going to compare each and every pixel whether it is lying on the line or not. If I have two pixels, one line can be drawn and all the remaining pixels can be compared and can be checked whether they lie on the line or not. If I consider 3 pixels and 3 pixels, using 3 pixels I can draw how many lines? 3 lines I can draw. So here, by drawing the 3 lines, I can check all the pixels whether they are lying on any of the lines, any of the 3 lines. And if I have n lines, n pixels, I can draw how many lines? N into n minus 1 by 2 lines, or almost n square lines I can draw, and each and every pixel must be compared with all the n square lines, and then I am going to decide whether that particular pixel belongs to that line or not, or that edge or not. And it will be a difficult process to compare all the pixels with the lines by drawing all the lines. So therefore, One possible solution is to first find all the lines determined by every pair of points and then find all the subsets of the points that are close to particular lines. It is one possible solution. And of course, it may not be possible every time. Therefore, we go with a simple solution for that half transform. Half transform says that says what? For example, I have the pixel xi yi, another pixel xj yj. If I draw the straight line, so my target is what? By taking all the rest of the in the image, let us take n pixels. That is, in the rest of the image, we have n minus 2 pixels, right? So all the pixels must be checked whether they lie on this particular straight line or not. Straight line or not, right? So here it is a very difficult thing to check. Difficult thing to check, right? So therefore, what we do is first we take the pixel xi yi, the half transform xi yi. So here, if I take xi yi, I can draw a line which is passing through xi yi with some intercept b is with slope a and intercept b is yi equal to axi plus b. It is a general straight line equation which can pass through any point xi comma yi and with the slope a and with the intercept b, right? So here, instead of checking all the other pixels whether they lie on the straight line yi equal to axi plus b, I'm going to rewrite the expression with respect to parametric space. That is, instead of writing the expression for y, I'm going to write the expression for b. B equal to minus xia plus yi. So here xi and yi are becoming constants now. B and a are becoming variables. So that is, for different values of slope and intercept, I am going to different values of a and b, I am going to draw the lines which are passing through xi and yi. So here, for this, b and a are changed. If I go on changing here, similarly here, if I draw b, if I draw the similar way, if I draw the lines for xj and yj, and the two lines may that is the lines which is passing through xi and yi and the line which is passing through xj and yj may intersect at one particular point, and at that particular point the slope value may be a dash and the slope intersection value may be b dash, and these two are the values for both the equations. Not only both, if I draw n lines, if n lines are intersecting at this particular point, then you can say, and those n points are uh, related to one particular edge. Like that, you can identify the similar points on the edge. So for that, what we do is we take the parametric space. But anyway, here the drawback here is, if I take if I take the similar pattern, if I draw a line which is a vertical line here, so what is going to happen here? The vertical line, if I take, that vertical line will have v dash equal to 0. Nothing will happen. But if I take horizontal line, slope will be equal to 0. Slope will be equal to 0, and it leads to infinite values. Right? So here, therefore, to avoid this confusion, we are going to take the parametric space. Instead of taking the straight lines, I'm going to take the parametric space using theta and rho. That is, I'm going to take polar coordinates. So that is, I'm going to take the polar coordinates theta and rho. The half transform consists of finding all pairs of values theta and rho which satisfy the equations that pass through x comma y. So earlier I used to take a dash a comma b. By changing a and b, I am going to take the straight lines and the intersection points. Now I am going to take the values of theta and rho. By changing the theta and rho, I am going to identify the intersection points. But anyway, if I change A and B, I'm going to get the straight lines. But here, if I take theta and rho, changes of theta and rho, I'm not going to get the straight lines. I'm going to get the sinusoidal equations, right? So therefore, the intersection points can be considered as the intersection of sinusoidal points, right? Sinusoidal signals, I can say. And it is the intersection point of 1, 4. And 1, 4 belongs to 1H. And here 1, 3, 5 belongs to 1H. 2, 3, 4 belongs to 1H. Like that, I can decide the edges using Hough transform. It is a resultant taken from your Gunjali's textbook, an example, a real-time example taken here. First infrared image, it is the infrared image, and after applying the gradient here, so it is the edge detected here. And if I apply the Hough transform, and it is the Hough transform, and here the linked pixels. So these are all linked pixels here, linked pixels, and here there is no other pixel which is linked to the edge of this particular image, right? So finally, how do you process or how do you apply the Hough transform? First, an approach based on Hough transform is compute the gradient of the image, the first step, and threshold it to then obtain the binary image. Just now we have seen, so it is binary image. By applying the threshold and just converting into the binary image. Next, specify subdivisions in the row data plane. That is the next task. And the next one is examine the counts of the accumulator cells for high pixel concentration and examine relationship between the pixels in the chosen cell. Just now I have explained the procedure. And the next one is, one second. Right. Thresholding. Here in the thresholding assumption, for example, you know about thresholding. So the thresholding is also discussed in the very first chapter, in fact. But anyhow, the thresholding is also used to separate the regions or separate the areas. For segmentation, we can also use thresholding, right? That range of intensity levels covered by objects of interest is different from the background. For example, here segmentation is what? Whenever I capture the image, sometimes I need to separate the foreground and background. Then only I can identify the object. Basically, the threshold is used for this particular purpose, that is separating the foreground and background, right? If the image is taken, it is the background, it is the foreground. And here, if I apply the threshold to particular value, this particular background can be separated and the object can be separated, right? So that is the way we use thresholding for image segmentation, right? If I take T as a threshold, above T one part can be considered, below T another part can be considered, right? Even I can use multiple threshold. If I have based on the application, we can use multiple thresholds also, right? So usually here, so how do you take the image by how do you capture the image, and on what parameters that particular image depends? In the very first chapter we have seen, it depends on reflectance and illumination. Reflectance and illumination. Here the threshold can be decided based on this particular reflects and illumination, and you can draw the histogram for deciding the threshold. For deciding threshold, you can draw the this particular histogram, right? Already this part is there in the very first chapter, in fact. Another one is basic global thresholding. So in the global thresholding, we follow a particular procedure. First one is general thresholding. We take either two thresholds or multiple thresholds, and I'm going to check whether the pixel is having the intensity value less than this particular threshold or greater than this particular threshold. Based on that, I can separate the regions. I can segment the regions. It is general thresholding. Global thresholding in the sense, first we take one estimate, initial estimate T, segment the image using the threshold first, and this will produce two groups. One is G1, other one is G2. And one G1 is having the pixel values which are greater than threshold value. Another one is having the pixels which are greater than less than the threshold value. Two groups. And after that, what I am going to do for the perfect segmentation, compute the average gray level values in the regions which are separated by a threshold. One G1, another one is G2. Here I am going to find the average value. Let it be mu1. Here I am going to find the average pixel values, that is mu2, right? And after finding the mu1 and mu2, I am going to decide a new threshold. That new threshold is nothing but t equal to 1 by 2 mu1 plus mu2. Again, the step 2, repeat the same 2 to 4 until the difference in t in successive iteration is smaller than a predefined parameter t. That is, so if you go on continue the same process at one particular point, if you compare the t with the previous t, the change is very, very little change. Then you can say, yes, it is the perfect threshold to separate the objects. And here you cannot take direct the threshold, you cannot decide threshold value like anything, and sometimes it may leads to wrong decisions and wrong solutions. So therefore here it is better to go with global thresholding, right? Otherwise global, and other one is adaptive thresholding. Adaptive thresholding in the sense, and based on the situation, adaptive. First you take one threshold, no, it is not giving particular result, and then change to another threshold, and then change to another threshold. That is, here one way, at one particular part of the image, one threshold you can take, another particular part of the image, another threshold you can use, and another particular part of the image, another threshold you can use. And everywhere you are not going to use one threshold for the entire image, right? So another one is optimum global and adaptive thresholding. So here the thresholding process, that may be global thresholding, that may be a normal thresholding processes which we have discussed so far, are deciding the threshold based on the pixel intensity values. And you can also take the threshold value using the probability density functions. This method treats only the treats pixel values as probability density functions. The basic goal of this is what? Minimize the probability of misclassifying pixels as either object or background. For example, here I have this particular part of the image. If I consider the pixel here, you may be in a confusion that whether it belongs to the background or it belongs to foreground. You may be in a confusion for some pixels. Here the major idea in the application of the optimal global and adaptive thresholding is the removal of such, that is the pixels which are in dilemma, and sometimes the pixel which must be there in the background may be considered as the pixel in the foreground, or some pixels which are supposed to be in the foreground may be considered as the pixels in the background, and those pixels must be removed. And that process will do in this particular thresholding process. Another method is region-based segmentation. In the region-based segmentation, the edges and thresholds sometimes do not give good results for segmentation, right? Edges, first one edge detection, other one is using threshold segmentation is done. So therefore, what we are going to do is we are going to do the segmentation on region-based, right? So here, how do you decide region-based segmentation is based on the connectivity. Connectivity in the sense what? Connectivity can be decided based on the similarity of the pixels, right? So each region must be uniform. So we are going to separate the regions, and the region must be uniform. Uniform in the sense what? So all the pixels must be connected together, right? That is called uniform region. Connectivity of the pixels within the region is very important here. So in the region-based segmentation, basically we take two methods, two approaches. One is region growing, other one is region splitting here, right? So in the region growing, here in the region growing, it is the procedure we follow. For example, if R is the entire image, that image must be segmented into regions. That is our target here, right? How do you segment the image? And you are going to segment the image RN. So in that Ri, if I take the union of all the regions, again it should be equal to the entire R. In that way, you need to separate the regions, right? That is the first condition. And the second condition is Ri is a connected region. That is, all the pixels in the Ri must be connected. Connected in the sense what? Must be similar. All the pixels must be similar. And at the same time, the two regions must be disjoint. Disjoint in the sense there is no common, there is no pixel in the Ri is in connection with the pixel in the Rj. And at the same time, P of Ri must be equal to true. And at the same time, union of Ri and Rj must be equal to false. That is, there is no such. These are the conditions we need to follow in the region-based segmentation, right? Another one is, first one it is called region growing. Second one is region splitting. So opposite of region growing. So first there is a large region, and then predicate is used to determine if the region is uniform or not. For example, if it is not uniform, it requires that the region be split into two regions. For example, first uniformity must be checked. If the entire region is uniform, it can be considered as a single region. If non-uniformity is there, again divide into two parts and then check individual regions. And if there is uniformity, yes, it's separate region. Again non-uniformity, again split into two regions, right? Until you get the uniform regions, the splitting process will be followed. First one is separating the pixels and deciding the regions. Just second one is, that is region growing. Individually we are growing the regions. Second one is, by considering the entire region, we are splitting. Right? So this is the procedure, region splitting, right? Region growing and region splitting. So here the segmentation can be done based on by detecting the discontinuities, or by using the thresholding, or by using this particular region based segmentation. So by in the detection process, we also use edge linking and boundary detection process. First, detection of discontinuities, edge linking and boundary detection is used for segmentation. Second, thresholding is used for segmentation. Third, we can also use region based segmentation, and where either we can grow the regions or we can split the regions based on the uniformity, right? So it is the complete segmentation procedure we follow in the image processing, right? Thank you. And here the textbook you can follow for this particular chapter is Gonzalez, beautifully explained in the Gonzalez textbook, right? Thank you. I think you have the class, one more class at 12 by Kishore sir. So therefore I'm just leaving the meet. I'm just leaving from the meeting. Thank you.